seminar speaker. Thank you. I should announce that this seminar will be recorded. Mario received his PhD in applied plasma physics from MIT in 2013. And his PhD work was on the observation and measurement of self-generated B fields from ablative Rayleigh-Taylor instability. And he won Marshall Rosenberg Outstanding Doctoral Thesis Award for his work in 2014. And then he won another fellowship, NASA Einstein postdoctoral fellowship, which he did at University of Michigan, where he worked on laboratory astrophysics and study of magnetized jets. Now he's a research scientist at General Atomics, and he's working on a variety of topics, including inertial confinement fusion, laboratory astrophysics, radiation source development, and of course, MAG-LPI for CMEC. And he will be talking about his work on Collisionless-Weibel filamentation under varying plasma conditions. Thank you, Mario.
Great, thanks Farhat, and thanks to the organizers for inviting me to come and talk at the CMEC seminar. So what I'm actually going to talk about today is a series of experiments that we did a while ago and that we brought back to do more analysis and try and understand the data a bit more within the center. And so I'm going to say right off the bat that a lot of the work here was done by Swarvanu Ghosh and Ram at UCSD and Marissa Adams at University of Rochester. And I'll point that out as we go through, but that really made their contributions really made this story possible. And it's still evolving. We're trying to get to the bottom line here, and I'll give you sort of the story of this data and these new types of analyses that we've come up with to try and look at this type of information. The collisionless shock collaboration has been going on for, I don't know, over a decade now. And so there's lots of data out there, different types, and looking at different aspects of Weibel filamentation. We'll touch on all of that in the presentation. And I guess I'd like to say that, you know, if you have questions during the presentation, I'm totally fine with being interrupted and discussing things. I'll give my best to answer any questions you have. I want to make sure things are clear. I know that this is a lot of this, it'll be new types of experiments, new types of physics for a lot of you. So feel free to raise your hand. I'll try and keep an eye on the chat. I definitely don't have 55 minutes worth of material to hear myself talk. So please ask questions along the way. All right, so with that said, then on my title slide here, I'm showing the kind of the big pieces of data that were taken for this study. And so what you're looking at here are processed proton images where we've done analysis to pull out what the path integrated magnetic field is in different types of plasma flows that are interpenetrating. And so let's see here. Can you guys all see my mouse? I think you can see it. So on the top row, we have 8 millimeter separation. We'll go over what all this means in the presentation. We have foils separated by 8 millimeters or foils separated by 5 millimeters, and 3 different types of material. So plastic, aluminum, and copper. And what you're looking at here, white is the positive, we'll call it the positive direction, and it's in 3 kilotesla microns. The bottom is negative 3 kilotesla microns. And so what you can see is you get these oscillations in path integrated magnetic field in these systems. And we want to pull out some quantitative information from that so we can compare that with analytic theory and see how well we understand what's going on in here. And so let's see, is it click? There we go. And so we'll go over this plot in more detail towards the end, but I just want to give you kind of the punchline at the beginning, which is when I plot what I infer from the data. That's the FFT, fast Fourier transform inferred magnetic field from data here on the y-axis, and what I call saturated B field strength, or B star, from flash calculations on the x-axis. The dashed line is a 1-to-1 if everything were exactly lined up. And given all the assumptions that go into this analysis and the large variation in uncertainty in the error bars, what I call this is decent agreement, in that the numbers, the magnetic field strengths that we're getting from the data agrees well with what we'll say is the linearly saturated value of the magnetic field. And we'll get into what all that means. And so as we go through the presentation, because there's a lot of different data here, the 5 millimeter separation cases are always highlighted in red, with each symbol presenting a different material, and then the millimeter separation cases are always highlighted in blue. And so there's a lot of information on all this. So we'll try and keep it straightforward as we go through it. So this work is possible because of all of our collaborators. Like I said, during the center,
Yeah, he froze for me too. It looks like he lost his connection, so we'll just give him a minute to come back. Hang tight with us. Sorry, everybody.
I'm just going to call him. Yeah, I just spoke to him. He will be joining in a minute. Miriam, perhaps you can stop recording until he comes back.
Yeah, that's a good idea.
a long time thinking the internet at the office is going to be better than home, and this is what happens, of course. Okay, so I feel like I probably lost you guys somewhere back here. Did I?
It was the next slide, I think.
Okay.
Yeah, this one. Yeah, the end of this one.
We'll thank all of our collaborators, and then we'll go on to the outline. Okay, so coming back to it then. So the outline for the talk, we'll discuss the astrophysical motivation and where collisionless-Weibel instability is thought to play a role in astrophysical systems. I'll talk specifically about some of the analytics and basics of the ion-Weibel instability in electron-ion plasmas, because that's relevant for both astrophysics and the experiments that we're doing. We'll discuss the experiments we've done at Omega to look at this, and then the new analyses that are really novel for this presentation is its fastest growing mode analysis that we'll do for using benchmark flash calculations, and then how to pull quantitative information out of proton images to compare with theory. And that's what we'll talk about at the end. So the ion-Weibel instability is a leading candidate mechanism that can mediate shocks in astrophysical plasmas. So I grabbed a couple of pretty pictures here from the astrophysical library showing Cassiopeia A, the supernova remnant. What you can see here in these little light blue kind of streaks around the edges are actually the emission from a shock wave. And you see about the size of those, that shock, and the mean free path in this system is about the size, the diameter of this system. Similarly, you get collisionless shocks in the pulsar wind nebula, say in the Crab, or in gamma ray bursts shown here. And so the way that shocks are typically created, the way that we think of them is through the pileup of pressure waves, and then the shock is actually mediated or created through collisions between the particles in the fluid. And so the thickness tends to go something like the mean free path of these collisions. And so, for example, in the Cassiopeia A system, right, you can see how thick the shock is by the thickness of these blue wisps, but the mean free path is much larger. And so again, in many astrophysical objects, the mean free path tends to be a lot larger than the scale of interest. And so we term these shocks as collisionless because they're not mediated through typical collisions that we think of when we see shocks. The other thing that collisionless shocks are interesting for is particle acceleration. So this is a video from NASA that I got from one of my collaborators, George Swadling, that he used for one of his presentations, but I like the video a lot. And so it shows the kind of diffusive bouncing around pattern that a proton and an electron might have in a collisionless shock in astrophysics. And so what happens is you can get what they call diffusive shock acceleration or first order Fermi acceleration. And the way this works is particles are bouncing around and reflected off of magnetic mirrors that exist within this within the shock, gaining energy with each bounce. And the resulting particle energy spectrum takes the form of a power law. And so one of the hypotheses is that collisionless shocks and first order Fermi acceleration processes are responsible for some of the highest energy cosmic rays that we see in the universe. The ion-Weibel instability will mediate shock formation in simulations of astrophysical plasmas. I'm showing here some results from Kato and Takabe that they published in 2008. The top panel there is density, where the color bar represents the density of the plasma. And you can see all the way on the left upstream, it's fairly uniform. And as the plasma collisionlessly interacts with the background, you get these filamentation, this filamentation instability in the density, eventually going to a full form shock all the way on the right. And so a line out from this simulation is shown on the bottom, where the density is plotted with the left axis, normalized to the upstream density. So you see it's at 1 right early on. And even as the filamentation begins, the average density is about the same. As the filaments grow larger and larger, you start to build up a shock front. At the same time, you watch this magnetic energy shown here on the bottom thin line starts to ramp up as you approach the shock front. And in the particular case that they simulated here, right, you have a density jump of 4 across this shock. So you have a strong shock. The magnet, just to give kind of scales, the magnetic energy relative to the kinetic energy is shown here. And so, at the shock location, you're looking at something that's maybe like 0.2, 0.25-ish of the kinetic energy. And so that's like your plasma beta, if you want to, ram pressure beta, if you want to think of it that way. So now we'll talk about the ion-Weibel instability in electron-ion plasmas. So magnetic field structures can form within an initially unmagnetized collisionless interpenetrating plasma. So these are 3D simulations done by Federico Fusa using OSIRIS. These are done from 2013, but I like the videos, so I keep them in my presentation here. I think they illustrate what we're doing in the lab very well. So on the top panel, you'll have density and the color bars shown relative to the initial density and not. On the bottom panel, you have magnetic field values with blue being the negative and red being the positive direction. It's normalized to mv squared. So in these simulations, the two flows run into each other and interpenetrate. Again, in the density images, you can see the density filaments starting out with somewhat short wavelengths. They go to longer wavelengths in the center. They eventually kind of all merge into this, big shock formation. But you can see how it starts off with small filaments and goes to larger filaments in density. And the same is true in the magnetic spectrum. So again, filaments start off small. You start to get merging, and you get these larger and larger magnetic field structures as the shock develops. So one of the questions I get often is about the electric and magnetic fields in these systems. So I want to put a plot here from Charles Rouillère, his Physics of Plasmas in 2015. And the point here is that electromagnetic energy is dominated by B fields through most of the evolution, and is roughly constant throughout the nonlinear phase. So we'll go through each of these plots here slowly. On the top left here is the electromagnetic energy. So these are from 2D PIC calculations. So the black is the electric field in the longitudinal direction. The red is the electric field in the transverse direction. So particles are flowing in the X direction. And then the blue is the magnetic field in the other transverse direction. Okay. So early on in time, when you have electron ion plasmas running into each other and interpenetrating, you get the electron collisionless-Weibel instability starts first. It has much faster growth rate, and it actually tends to give relatively high electric fields right at the very beginning here. So this is normalized, so don't think too hard about what these units are. And then time is on the x-axis here. Again, this is normalized to here to the electron plasma frequency. But you get this initial phase dominated by the electron-Weibel instability. And what happens there is it quickly, the electrons isotropize their energy quite fast, and then we'll eventually end up heating the ions. If you look right below that, this kind of illustrates it. So this is the mean velocity in the x direction, so that's the direction they're colliding into each other. Here, black is PIC ions, blue is PIC electrons, and then there's a couple of different nonlinear theories that it's compared to. The point is that in the blue line here, so this is the PIC electrons, right? It starts off with 0.2 C, and within the first few cycles of the electron plasma frequency, the electrons are already starting to isotropize and lose their directed momentum of the flow, and that goes on throughout the nonlinear phase. Whereas the ions, on the other hand, tend to keep their momentum for a much longer time, and we'll talk about this a little bit more. So now back to the electromagnetic energy plot. Electrons tend to start isotropizing over these first few hundred T omega PEs, and then the ion-Weibel instability will start to take over. As the electrons isotropize, they're losing their bulk velocity, and that's what you need to keep this collisionless interaction going. And then the ions will start to take over. So it's a much slower instability, but it starts ramping up over this time period for these particular parameters. And really the magnetic field tends to dominate the electromagnetic energy until magnetic saturation, which is occurring when the B field that the filaments are creating actually starts to stabilize and dampen the growth. And so when this occurring when the ion quiver motion within that magnetic field starts to approach the dominant wavelength, which I call capital lambda W here. So that takes me over to the top right panel here, which is the dominant wave vector. So this is normalized K as a function of time. Again, here the black solid line is PIC, and the dashed lines are a couple of different nonlinear theories. And so what happens is the dominant wave vector starts, we'll call it high here in the electron area, and as the ions start to take over, the wave vector amplitude or magnitude is decreasing. And so what's happening here is the dominant wave vector wavelength is getting larger as a filament, just like we saw in those videos above, right? The filaments start small, and as you go into the nonlinear regime, they start to merge, and you get these larger and larger wavelengths. And so that's what's represented here by this solid black line. And then the dashed lines here are different nonlinear models. The one I'll talk about a little bit more later is the dashed red line model, where it's a coalescence. So you have filaments which, after reaching that saturation point start to coalesce together to build larger filaments. And then the last one on the bottom is the transverse temperature. And so this is just, again, illustrating the isotopization from the electrons. So the electrons, again, electrons and ions start fairly cold. The electrons heat up quite quickly. By the time we're reaching the sort of nonlinear saturation point of the ion-Weibel instability here, the electrons and ions are roughly the same temperature, but they're much hotter than how they started out with at the beginning. So the nonlinear growth can be treated as a coalescence of current filaments, and that increases the magnetic wavelength of the instability. So that's what I was trying to highlight here with the black line. And then the coalescence model, the dashed red line, is shown to reproduce trends observed in PIC modeling in both 2D and 3D. And just a note, so not to take all of these numbers on the x-axis here to heart, the PIC simulations are often done at higher velocities than in the experiments, but that helps the evolution go faster, and you can scale those results by the velocity of the system. So we'll now talk about the experiments that we did at Omega and what that platform looks like. One of the main diagnostics that is used here to visualize magnetic fields is 15 MeV D3 helium fusion proton radiography. So here's a schematic from one of Chaney's papers of what the general platform looks like. You typically have two solid density disks shown here, top and bottom. Lasers will drive one side of each disk, creating a hot, fast supersonic ablation plasma coming off normally from the disk. The two plasmas within themselves are collisional, right? So the electrons and ions within each plasma plume are collisional. The bulk velocity, however, makes the intrajet jet-to-jet mean free path much larger than the system size for the ions, but for the electrons tends to be near the same order, which is why the electrons are still collisionless between the two flows. So, and then at some time later, a separate set of laser beams irradiates a D3 helium filled capsule with a 1 nanosecond pulse. This irradiates the outside and drives shocks spherically inwards. This heats up the gas and implodes and actually creates D3 helium fusion, and that gives us a roughly 15 MeV proton, which comes out in 4 pi. And then of specific interest to the experiment, those protons which come through and traverse through the two plumes that are interacting here, those protons are recorded on a piece of CR39, where we then count up each individual proton track and then plot. Here I'm plotting what we call normalized proton fluence. So that's I've normalized to the background fluence of the proton. So you can see at the edges in this particular image, you get back to the fluence going like 1. But at the midplane, you see all these structures where you have, big voids in proton fluence or big enhancements of proton fluence. And so those are all, those voids and enhancement in proton fluence are coming from the deflections that they feel as they go through this plasma in the middle and feel the electromagnetic fields inside. The stopping of the 15 MeV protons in here is way too low to do anything. It's low density plasmas. So all of the deflections that you see in these images are coming from electromagnetic fields within the plasma. And then the primary data set that we'll talk about, right, is the plastic, aluminum, or copper foils, and then separating them by either 5 millimeters or 8 millimeters. By pushing them closer together, what you're doing is making the density higher when the plasmas hit the center, because there's less time for them to expand as they go towards the center, and they're also moving faster. So you're changing some of the basic plasma parameters there, density and velocity, as well as ion species by changing the material. So 15 MeV proton images at the midplane visualize nonlinear evolution of magnetic fields between plastic foils separated by 5 millimeters. So this is a data set that Channing published in 2017 from the same shot day, where we looked at the temporal evolution of the CH plasma only. So this is a 5 millimeter separated CH foils at 3.2, 4.2, 5.2, and 6.2 NS. And so at this earliest stage, when the fields are just starting to really be visible in terms of these filamentary structures, this is already laid into the nonlinear regime in terms of time frame based on the, if you think back to the PIC simulations that we saw a second ago, while the fields are quite small once it's even reached that phase, in order to see these filaments, we wait until about this long. And then by looking at later times, you can see that the filaments start to merge. You're starting to see larger filamentary structures in the proton images as we go forward. And at the latest time that we sampled at 6.2, you're actually even starting to see a lot more longitudinal structures in the magnetic fields, in the proton images, excuse me. And so the additional experiments that we did in this configuration, we've then buried the foil materials using aluminum and copper as well. The plasma conditions at the midplane of all the configurations are measured using Thomson scattering. So what I'm showing here are results from Thomson scattering measurements for the 6 cases that we've been discussing. On the left is electron density as a function of time. On the right is electron temperature as a function of time. And shown for reference here is the laser drive for the 2 foils. And the dashed lines here represent when the proton images were taken for this material scan study. The error bars here that are shown are not actually errors, they're variants. And so the Thomson scattering is done in a streak manner. So we take data for 1 nanosecond for each of these points. And what the vertical error bars represent is how much variance you get in the Thomson scattering data as you look at each of these different times. And so again, the red symbols are for 5 millimeter separated cases, and the blue symbols are the 8 millimeter separated cases. So densities for 5 millimeter tend to be sort of few 10 to the 19 in most cases, and few 10 to the 18 in the 8 millimeter separated case. And temperatures tend to be sort of around 1,000, 500 to 1,000 for most of that, depending on which time and plasma you're looking at. So we use the Thomson scattering data to benchmark modeling, specifically flash calculations, to understand the full temporal evolution of the plasma from the very beginning. And we do that so that we can do a fastest growing mode analysis as a function of time. And so what I'm showing here are what I call single flow overlapped flash simulations. And I'm comparing them with the 8 millimeter CH and aluminum cases here for reference. So what each of these lines are is a flash calculation assuming a different laser absorption onto the foil, and the blue squares are the data, or the blue triangles are the data for the velocity. So plastic is on the top row, aluminum is on the bottom row, and then we have density on the left and velocity on the right, as right from the ion wave feature in Thomson scattering. So what we're trying to show here is that we take a snapshot with the Thomson data at some point during this evolution. And that being said, the plasma has been evolving and interacting for a much longer time. And so you can see what kind of density variation or velocity variation you might expect at the midplane, given that the plasmas that we're using for the experiment are spatially varying, or spatially and temporally varying. So if you sit at the midplane, you watch a host of different plasma conditions pass by you, okay? And the question is, all right, well, if that's the case, what is the right plasma that is setting the Weibel instability? All right, and we'll get there. So the fastest growing mode analysis is performed using density and velocity profiles from flash. What I'm showing here is just to get you an idea of what this looks like for a particular set of parameters. This is a figure from Ryutov 2014, where he does a nice job of showing the ion Weibel growth rate and includes collisional electron effects in there. And so using that same dispersion relation, you can solve for the growth rate here on the y-axis as a function of K. And each of these lines here was for a different ion temperature. And so you can see that in each case, there is a peak, and it eventually goes back down to 0. So there is a fastest growing mode. And depending on which plasma condition you get, you'll have a slightly different K vector that you would expect to be the fastest growing mode, okay? So if I do that for the CH 5mm case, we'll use as an example here, and I do that same calculation with the plasma profiles from FLASH, and calculate what the dominant wave vector is at each instant of time at the center point, I will get this this black line. Okay. And so it's peaking somewhere around 200, and as the density is going up, so the way that the dominant wavelength scales is like 1 over the ion plasma frequency. So that's something like square root of mass over Ni, which is Z&E. And so as that density increases in the midplane, the dominant wave vector is going to decrease and it's going to fall down. So depending on where you're looking in time, you would assume you have a different dominant wave vector from this kind of an analysis. In that same calculation, you also can calculate the growth rate, capital gamma W, which scales like this. So there's a velocity involved in that one, and what we call the saturated B field B star. Remember that the saturated magnetic field occurs when the ion quiver motion within that magnetic field approaches the dominant wavelength lambda W. And so those are plotted here. The orange line is the growth rate, gamma W, and the blue line is the saturated B field of B star. And you can look at them and you see that they scale similarly. And so that's why they kind of follow each other for the most part. And so again, you can see that the growth rate starts at sort of like 2-ish, 2 or 3 per NS and ramps up all the way up to 6 as you go later in time. Magnetic field strengths tend to be on the sort of like few Tesla range up to almost 10 Tesla in this case. And so there's a lot of variation just in looking at the temporal evolution of the plasma state at the midplane. Okay. And then for clarity, I've also plotted here the mean free path of the ion-ion intrajet ion-ion mean free path as a function of time. And you can see that in this case and in all the cases, we're in a very collisionless regime. As the plasma slows, you start to approach more the foil separation, so you're starting to get more collisional down here. But for the most part, you're collisionless the whole time. And so the initial the initial saturation point, right? As we were talking about before in the PIC calculations, the linear saturation, that is when the B field starts to the ion quiver motion in the B field starts to approach that dominant wavelength. It only takes a couple hundred picoseconds or a few hundred picoseconds, depending on which plasma we're looking at. And so what we're saying then is that during that first interaction, when we can't really see anything, the plasma is a bit low in density to make a measurement. B fields are not quite, the scale length of the B fields hasn't got big enough to start measuring. Is hard to kind of see. But we're saturating at this early time, again, given the kind of timescales that the growth is going at. So within that first 400 picoseconds or so, we hypothesize that this is actually what sets the ion-Weibel spectrum moving forward, and that's the part of the plasma that we actually care about to look at the analytics of scale size and B field strength. So we can do that analysis for all the different cases. And the fastest growing mode analysis then suggests very little variation, but some in the magnetic field wavelength and the saturation strength. So the wavelength is on the left-hand side, the saturation strength is on the right-hand side. And I've plotted the dots with the variation expected from that first, 400 or so picoseconds, what kind of variation you would expect in lambda W and B star. And in some cases it's bigger depending on what the plasma profile tends to look like. And it has this kind of variation. And so these analytically derived values from the first 400 picoseconds of the interaction can now be compared with experimental observations of wavelength size and inferred B field strength if we can pull these quantitative numbers out of the data. So we've come up with a Fourier analysis technique to look at proton images. A lot of this is based on some work that Levesque did. So I'm showing a figure from Levesque's POP in 2019. And so the B fields driven by the ion-Weibel instability are visualized with proton imaging. And so one of the things that's kind of hard for people to wrap their head around is like, how are the protons actually observing these B fields? Clearly we do, you see them in all of the data. And so what Joseph did was looked at counter streaming plasmas as they drive Weibel filamentation, and he represents this by alternating currents, which is proportional to essentially the vector potential AZ in his coordinate system here. So the blue and red lines, or filaments here rather, represent currents in different directions. And so these are the Weibel filaments. Essentially, you can imagine having your two foils on the top and bottom. These would be the filaments that you would create, something like this. Okay. And then as the protons go through them, you see this, this is a line out representation of that, but you see this modulation in proton fluence as it goes through this sort of forest of filaments. And what you actually find out then is that the proton velocity that's parallel to the filament axis, so in this case, the vertical component of velocity, is sensitive to the azimuthal fields, because each of these currents is creating little azimuthal fields around it, right? And so it's actually that vertical component, the diverging source, which is giving you the ability to view these azimuthal field structures. And that this forest effect of going through all of these different filaments is actually imprinted within the first few layers of the system. So on the top here is a sort of a top-down view of all of these different filaments, again, red and blue being in opposite directions. He hasn't put it 100% packing ratio, it's just as an example. And then what the path integrated AZ would look like, because the proton imaging is always going to be a path integrated measurement. And what it's sensitive to is path integrated B field, or the path integrated vector potential here. And so what he's showing here is in the top right is the amplitude of path integrated AZ. And you can see that within the first couple layers of these filaments, you've actually set your modulation in path integrated AZ pretty early on. And he's done this for a bunch of different filament sizes and densities. And so it's a really useful paper when trying to wrap your head around the complex forest of filaments that you're actually looking at with proton imaging. This still assumes a small angle deflection, and for the 15 MeV protons, this is valid for roughly 50 Tesla for B fields less than about 50 Tesla. So now that we kind of understand a little bit of how these protons are sampling our forest of current filaments, the proton image is taken under the different plasma conditions, visualize B fields from the ion-Weibel instability under these different configurations. So again, the top row is 8 millimeter separation, the bottom row is 5 millimeter separation, and then you have CH, aluminum, and copper. And you can look at them, and all 6 of them look fairly different. There's some similarities in sort of scale size or amplitude in the proton fluence variation, but it's hard to say one way or the other what's really going on here. And so what Swarvano has done using the code developed by Archie Bott, it's discussed in the Journal of Plasma Physics paper here from 2017. It's the problem solver, and it's an iterative solver that retrieves the path integrated B field from proton images. So here's our sample normalized proton image. You run it through the problem solver, and it solves for both components of the magnetic field, and eventually coming up with what I've determined here, called BYL, where Y is going into the page, or BXL, where X is parallel and transverse, parallel to the page. And so you can kind of the BYL follows some of the filamentary structure that you see here, and this BXL is actually coming from this big red high fluence area up here, and it's being moved from down there, and so it's coming from what we call the BXL. For the filaments, what I care about here is the BYL images, so we'll focus on that. The convergence is assumed when the BYL range reaches an asymptotic value. So just looking simply at the range of BYL as a function of iteration number, you see at some point it starts to asymptote, and at that point we consider convergence being reached and stop the solver. So we've done this for all of them, and we see that the BYL amplitudes at relevant spatial scales reveal Weibel-driven B fields under different plasma conditions. As we saw in the proton data, we've now taken one step away from proton fluence and brought this into path-integrated magnetic field space. And so these are the 6 images that we showed on the front, the title slide, and going from plus minus 3 kilotesla microns. So the next step is to pull out the spatial component of this. And so our focus is at the midplane. So we take a line out and then do an FFT. And then I've plotted that FFT here as a function of wavelength rather than K. It's easier for people to picture wavelength than wave vector. And calibrated it so that this is in absolute units of path integrated magnetic field, BL. And so what you see is you see a couple of dominant modes, what appear to be a couple of dominant modes, somewhere around 300-ish in this case, and somewhere around 500-ish in this case, right here. But again, this is path integrated magnetic field, and recall that we said that the path integrated vector potential is imprinted within the first couple layers. So let's use the wavelength, assuming a somewhat tight packing ratio, that the layer is something like a wavelength long, just to get an idea of what the magnetic field at that particular wavelength would be. And so we divide that spectrum by lambda, so that'll weight heavier the lower wavelengths than the higher wavelengths, and what we see is a peak pop out. And so we saw this peak before, but it's yet larger because of the scale size scaling with wavelength. And so you have magnetic fields that are sort of on the order of a couple Tesla or so. But now you can use the spectrum to pull out both a dominant mode, a bandwidth for that dominant mode, and a typical magnetic field amplitude for that mode size. Okay. Now we can again do this on all 6 images, and so you see here the path integrated Fourier spectrum in kilotesla microns. Again, they're all on the same scale, and you see in some cases they're larger, in some cases they're smaller. There's a couple peaks around. You do the same scale length assumption by lambda, and you see everything, the dominant mode really pop out in this case. The CH8 is pretty wide, but for the most case, you always see this mode that pops out here. And then you can pull the spectral information out and plot it for each case. So here again on the left, I have the scale size, the dominant scale size, pulled off the proton images, and the magnetic field amplitude from the Fourier analysis. And you see some minor variation, nothing particularly intriguing. You can, but there is some differences, but the errors associated, or the width of the peaks tend to make all of these things kind of overlap. And some variation in the magnetic field, but again, there is a big the error here, the error bars here represent the variation in the B field from the Fourier spectrum, not the actual uncertainty, because you're assuming the scale size is lambda, and that could be off by factor of 2 or so. But now we have some values that we can at least compare with the analytic theory that we showed beforehand. So the FFT inferred filament size and B field strength are near or above the linear saturation values. So we'll start on the left. So this is the plot of the FFT inferred, so data-driven scale size from proton images versus the fastest growing mode from flash. And again, the dashed line here is the 1-to-1. And so what you see is that even from the fastest growing mode from flash, we're assuming we're using the 400 picosecond first initial conditions of the plasma, that the data tend to be still a little bit larger, and so you're probably having some filament coalescence and such going on. On the B field side, there's a lot of uncertainty there in the scale size that you ought to use for the path integrated field. Again, I've chosen lambda. but that's probably an underestimate. What you see is the B field, again, data on the y-axis, analytics on the x-axis. And the data is near that 1-to-1 line. It's a little bit high, but again, we've chosen a scale size that might be a little bit small. But it's suggesting that we've hit that, we've hit that the saturation value, and it's holding strong there. So for fun, we also thought we'd take a look back at the temporal evolution, because all the other in the plasma study, the variation of plasma parameters, you're only looking at a single snapshot for a particular configuration. Hence the the need to kind of calculate what you might expect for each plasma condition and compare it with what we see in the data. In the CH case, we actually have a temporal evolution that we can look at. And so here's those same proton images that I showed before. I run the same kind of calculation to invert into path-integrated magnetic field. Note the difference in scale here is ±8 kilotesla, so that you could actually resolve what you're seeing at the later times. And then do the same thing at the midplane and do the Fourier analysis. Here you actually see at the later times, while you still see some of these smaller wavelengths, by far the dominant scale size is going to much bigger wavelengths, as you can see in the image, but it also comes out in the Fourier analysis, as you might expect. Also note here, the B fields have gone up. In this case, they're sort of in the 3 or 4 Tesla range at those later times. So this is something I put together recently over the last couple of weeks for this presentation, was to try and analyze these data and put it on a plot as a function of time and compare it with the fastest growing mode analysis that we did with Flash. So the dominant magnetic wavelength growth follows the trend suggested by the nonlinear coalescence model. And so what I've taken here is the black line is that fastest growing mode for the CH 5mm separation case that I showed much earlier in the presentation, and then applied the nonlinear coalescence model that Charles suggested in the 2015 POP, and assumed that these plasma conditions stayed constant, because that's how the theory was derived. So we'll just assume that for a second. And that's what each of these, the 4 lines that are shown here, are taken for the different plasma conditions, and assume that constant and let the nonlinear coalescence model evolve in time. And we get decent agreement. It's not quite the same, but it's given the assumption here of constant plasma parameters, I'd say we're really close. And what this again is emphasizing is the consistency of the data with the analytic theory, assuming you're looking at that initial interaction of the plasma. Again, 400 picoseconds, and doesn't necessarily have to be 400. That's just what I kind of chose based on the Flash calculations. So in summary, counter-streaming plasmas of plastic, aluminum, and copper are shown to drive the ion-Weibel instability. Proton images showed robust formation of Weibel-driven magnetic fields with different ions and under varying plasma conditions. What I found most interesting here was that we were able that the B field scale size and strength inferred from the data, which was the first that we've been able to do that, agreed well with the linear theory and the nonlinear theory as applied to the initial 400 picoseconds of the plasma conditions during the interaction. And that's kind of where we're at this point with this data set. So I'll take questions now.
Thank you, Mario. Appreciate it. There's one question in chat. Is the B field dependent on filament size?
The B, like the saturated B field?
I believe so.
Okay, let me just pull up the scaling there one more time. So I'd say not directly, no, it's not. In the formula, there is the dominant wave vector is in there, and so is the growth rate, and they eventually cancel out. And what it really depends on, so this is the reduced form of that in terms of what plasma parameters matter. The saturated B field is mostly dependent on the velocity and then the density, or mass.
Okay. Any other questions for Mario?
This is Bruce Remington.
Hey,
Very
Bruce.
nice. I missed